Hi, welcome to lesson 5 of week 2 of Julia Programming for Nervous Beginners, in which we talk about the type system in relation to multiple dispatch. And really, multiple dispatch is one of the really important things in Julia, and we do want to understand the type system well enough to explain it, but not anymore because it's actually a very big topic. So, what we really want to get to is that multiple dispatch matches the type signature of a function call to the type specification of a method. And to do that, we will need to understand that Julia's type system has concrete and abstract types, that there's a supertype function which can tell us when we apply it to a type what the supertype is, and when we apply it to a type, the subtypes function gives us the subtypes of that type. And finally, we want to understand that there's a type, an abstract type called any. So let us define the two double functions we had before. So we have a double of x, if it is int 64, is equal to 2x. And the double of x when it is a string is x repeated, just with 2. And now we can try to double 1.2. And that fails because this is of type float 64, and it's not a string, and it's not an int 64. And so the method that we have, these two methods, don't do anything for that. So what can we do about that? Well, we could try and make a third method for float 64, but Julia offers us something else which is interesting, namely abstract types. So there's an abstract type called number, and as far as Julia is concerned, an int 64, a value of int 64 qualifies as part of abstract type number, and so does a value of float 64. And so if we just change this to number, and then we try that, then it works. So now we can do it on floats. In fact, we could go further and define the default method, which is, doesn't matter what x is, we can say that is 2x. Now there are 4 methods, and this is a fallback method. So what happens is that this method is available when none of the others can work. So we use something which is not an int 64, it's not a string. In fact, it's not something that's any kind of number. For instance, a character. So what happens if we try to double a character? And then it says there is no method matching for character because we are trying to do things and that's int 64 and character. So that is going into this, and it's trying to execute 2 times character, which it can't. However, if we, instead of doing that, if we say that is our default, so this now is, if x is a number, it will be x to the power of 2, and if x is a string, it will be repeated. So let's try that, and that does work now. So the problem was not with the specification of the type, it was with the whether we're doubling it or whether we whether we're repeating it. If we specify the type any, we still see that there are still only 4 methods, and so these two are exactly the same. We'll explain later on exactly what the type any is. We've got to distinguish between an abstract and a concrete type. And an abstract type is simply a way of talking about several types at the same time. Whether they're abstract or concrete, we're just including them all in the one abstract type. So if a type in Julia has one or more subtypes, then it is an abstract type. We can check for this using subtypes. For example, if we look at number, we have subtypes number, and they are the types complex and the types real. So although int64 and float64 both qualify as concrete types accepted under the umbrella of the abstract type number, number is not the supertype of either of them. What we could do is we could keep on going. So let's say, well, clearly int64 and they are not part of complex, they're just real integers, and now we see we've got integer, and so under integer we can ask for that. It's still not one of those. Obviously our integers can have signs, so we look at that, and there we see we have int64 as one of the possibilities. So it's 1 to 8, 16, 32, 64. These are in alphabetical order, so that's why 1, 2 is before 1, 6, and 1, 6 is before 3, 2, and 6, 4 is before 8. You can instead start going down abstract float and see where float 64 turns up. So let's look at the supertype of complex. And we see that this is number, as we, in fact, it should be, because a number is the immediate supertype of complex. What about the subtypes of int 64? There are none. This is because int64 is a concrete type. It's something that can have an actual value. So integer is not something that has that can have a concrete value, and the type of integer, all it can have are subtypes. Its eventual concrete subtype int64, that can have an int64 type value, which we know is 64 bits. It occupies 0101 somewhere in the computer memory. There is no memory that can be occupied by anything of type integer. As such, the integer is merely an abstract type to contain lots of concrete types eventually. And any is its own supertype. So if we want to have supertype of any, then is it its own supertype. It is the eventual supertype of every single type in Julia, every single value. If you keep on asking for what is the supertype, what is the supertype, what is the supertype, eventually you must get to any for every single value in Julia. So what then happens when we have arrays? Well, Julia, as far as possible, tries to arrange that every element of an array has the same type. So if I ask for an array with the number 1 and the number 1.0, we see that we have an int and a float 64, int 64, float 64, but when the array is created, Julia wants them both to have exactly the same type. And the reason for this, of course, is that they are stored with the same bit or pattern. They both occupy 64 bits. And so arithmetic and storage and fetching and so on of this array is all done on exactly the same type of number. It can be done very efficiently. If we really insist, then we can say that we actually want this to be of a different type. So we can make this of the type number, and then it looks like that. We can even make it of the type real, and it still works. We can even make it of the type any, and all of them have the same values inside the array. But this is an array of type any. This happens to have two numbers in it. This is an array of type real, which happens to have one int64 and one float64 in it. And similarly, this is an array of type number. So they can be very, very different. So the possibilities of values that satisfy any and the possibility of values that satisfy number are completely different. And so when we want to change the array, we can change this array to contain strings, but we can't change these arrays to contain strings. We would have to change not only the elements in the array, but also the type of the array itself. And that's how Julia's type system enables multiple test sets. We can now answer the question, when a function has many methods, how does Julia choose which one to use? And the answer lies in the type system, and in particular in the idea of subtypes. So let's consider double of 7. So this is a function call, and there's an input 7, and the type signature is that there is one variable of type int64. Now, let's look at the many methods. Well, there are methods for int64, float64, and also for number. So there are 3 methods. I'm sorry, in my typing I seem to have left out the one that's x is int is number, but x can be int64, x can be number, or x can be any. So Julia chooses among those 3 the one with a more concrete type specification. In that case, it must be int64, because that is properly concrete. It has no subtypes. So number is a subtype of any, and it would choose, if it wasn't any int64 or float64, or number we would choose of the type number, not of type any. So how does it work? So when Julia calls a function, then what it has is that code is actually running, and all of the in the call, what is actually available to Julia are the actual values for that call. And so those values have a concrete type, and so the type signature of a function call consists entirely of concrete types. So now Julia searches among the methods in the type specifications for a match. So for each value in the type signature of the call, it searches for a match that matches that value, that is at first for that concrete type. And if it doesn't work for that concrete type, maybe there is a method in which it has a super type of that concrete type. So you go for the first super type, and if there is no method for that in the type specification, then I go one up, and I go one up until eventually I've tested all of them, and I hope that the value is included in one of the types for which there is a method. So ideally, this search above finds exactly one method. But here is an example in which, with 2 methods, in which it fails. So we have this type. If x is int64 and y, then we print in that x requires int64, y can be any. And if it's x and y is int64, then we print in x can be any, y requires int64. So let's create those. Disp type x, we specify int 64, and we don't specify anything for y, and so y is of type any, and so this is just printing us the message that x is So X requires, get our spelling right, int 64, Y can be any. And now we do it the other way around. We say that X is any and Y is int 64. And we say that X can be any, Y requires int 64. And now we disp type say for 7 and what are the examples? 7 and 7.0. And this works. It calls the first method. If we make both of them 7.0, then it says there is no match. There are two floats, and at least one must be an integer, so that's not going to work. And now if we say the second one is the integer, so first the first one was the integer, now the second one is the integer, and that works. And finally, if we say both of them are integers, then it says, oops, no. There is ambiguous. The method error, the disp type int64, int64. If we call the function with two int64 values, then it matches both definitions. And so what they suggest is that we define a method which is for two int64s. That would indeed be a good solution, but it's not necessary for us to do it now. So a part of your job as a programmer is to make sure that all of your methods apply exactly where and when you want them to. On this course, that will be easy. So these kinds of difficulties, the dispatch, the multiple dispatch that is being spoken about here, that is to give you a sense of how Julia works as a whole. So that we actually not leaving anything out, we're just taking small steps, we're just taking a small step into the type system, but that allows us to understand how multiple dispatch works. So that gives us a sense of how Julia as a whole works, but we will use on this course only a small part of it. And that is because Julia's type system has so many different types. Experts know many of them. They actually create their own types. This is a very powerful system. It's at the heart of what makes Julia such a powerful and fast language, which is at the same time very easy to extend. But you will not need to specify type for your functions. And on this course, only a few exercises might ask you to do so. And so even a beginner can write code in Julia with no problem at all. You need not actually try to use types in writing your code. You need to understand types, to understand multiple dispatch, and to understand the error messages you get. But you don't need to use it. And that kind of flexibility is what makes Julia a very attractive language for ease of use and for beginners. So let's summarize this. Number is an abstract type, and the immediate supertype of a type is given by the function supertype. Number is an eventual supertype of int64 and float64. That means that it's not the immediate supertype of either of them, but it is a supertype of a supertype, etc., of both of them. If we keep on asking for what is the supertype, what is the supertype, what is the supertype of that, and what is the supertype of that supertype that we've just got, and its supertype and its supertype, eventually we're going to get to any, which is its own supertype. On the other hand, if we keep going down subtypes, we will eventually get to a concrete type which has no subtypes. All Euler's values belong to concrete types, and all actual computations are done with concrete types, that is, with values. What happens in multiple dispatch is that it's Julia's way of matching the type specification of a function method to the type signature of a function call. All the values in the call must match the type specification in the code of that method. However, this can actually lead to ambiguity, and it is the programmer's responsibility to get rid of the ambiguity. And that is the end of lecture 5 of week 2. Thank you.